those of you who don't know me, I'm Tanya. 2 weeks ago, during our research group meeting, Moises mentioned news about a quadruple star system that had been identified where there was a circumbinary disk that was perpendicular to the plane on which the binary stars orbited each other. And then a few days later, Dr. Diaz approached me about giving one of these seminars about that paper, and so fast forward 2 weeks later, here we are. So today I'm going to be talking to you about the little system that could. Yes, that is a play on the little engine that could. But most specifically, I'm going to be talking about the planet-forming circumbinary disk that was detected in a polar configuration around one of the binary systems, in this system in particular. So I wanted to give you all an outline so you sort of understand where this presentation is going. First, we're gonna go over a few definitions, mostly because about 1 second into my reading the paper, I was like, I don't know what half of these words are. Just kidding, it was like 2 words. And so I went ahead and Googled them, and I wanted to make sure that you all were comfortable asking like definitions of words. If I can't provide the definition for you, then hopefully somebody in the audience can. After definitions, we'll move on to talking about single star systems, in particular how stars and planets would form in a single star system, with our solar system as a specific example. And so once we finish talking about single star systems, we'll move on to binary star systems. And so I'll talk about, the things that are a little bit different as far as binary star systems go and planets forming in binary star systems. Once we wrap that up, I'll go ahead and introduce HD 988000, which was the system that was talked about in the paper that Moises mentioned. After I introduce HD 988000 and a few of the characteristics of that system, I will talk about how the system was modeled in the paper that I read. And then after that, I'll go ahead and summarize the conclusions that were made in the paper. So we start with definitions. The first thing I had to do was Google what protoplanetary disk meant, because it was in one of the subtitles, and I didn't know what it meant. So a protoplanetary disk is a rotating circumstellar disk of gas and dust formed around a young star or protostar. For those of you who maybe don't know, circumstellar means it's orbiting around a star. Then circumbinary, in this case, is referring to anything that is rotating or orbiting around 2 stars, like a binary star system. And then we have a protostar, which was mentioned up there, and again, I was like, what does that mean? So a protostar is a young star that's still gathering mass from its parent molecular cloud. So moving on, we're going to talk about single star systems again. We're going to specifically focus on how stars and planets form in single star systems. And we're going to emphasize our solar system as an example. So the first thing you need to have a single star system is a star. So I'm going to review how a star is actually born. I hope you get that reference. It's a pop culture reference to Lady Gaga. So how a star is born? Well, first of all, you have a spinning cloud of interstellar gas and dust. If this spinning cloud is star forming, it's called a molecular cloud. And so this cloud is spinning very, very rapidly. Gas and dust will start coming together. And so as these clumps begin to form, the density of these areas causes the cloud to start collapsing in on itself in those areas. And so as the cloud collapses in on itself, remember that this cloud is rotating, and so the conservation of angular momentum causes this cloud to spin faster, because again, the mass is moving closer to specific points. And so we have this cloud that's collapsing, and as it collapses, it spins faster. And as it spins faster, it causes the cloud to start spreading out into a disk. And so now we have this protoplanetary disk that's forming. The protostar will continue to form at the center of this disk. And then eventually, the protostar will reach a density and temperature that allows hydrogen fusion or nuclear fusion to efficiently occur. And so at that point, the star has formed at the center of this protoplanetary disk. So where have we seen this, or not necessarily seen this, but one of the systems where we know that this occurs is the M42 system, or also known as the Orion Nebula. And so the Orion Nebula is actually the closest stellar nursery to our solar system. Stellar nursery meaning, you know, that a bunch of stars are being born in this cloud of gas constantly. This is actually M42, and right back here you see, I believe, M43. But anyway, there are approximately 700 stars that have been detected within M42, and they are all at different stages of star formation. And there have been several stars identified within M42 that have protoplanetary disks orbiting them. And so if there are protoplanetary disks, there should also be planets forming. And a few of these stars, in fact, do have planets orbiting around them. And so the next topic is about planet formation, right? Because now we have a star that's formed, but we don't have any planets that have formed yet. And so we have a protostar, or a star that is being orbited by a protoplanetary disk. What's next? Well, the dust in the disk begins to consolidate. And so these dust, they start off as particles, but then these dust particles start to come together and they begin to sort of collide and eventually become the size of, anywhere from the size of the moon to the size of Mars. And so these objects begin to collide to form larger planets. And in fact, this is how it's theorized that the Earth was formed approximately 30 million years ago.
I think the numbers is small, isn't it?
Yeah, I think so, but maybe there was another
order. Yeah, is it a different order?
My understanding is 4.6 billion.
Huh?
4.6 billion?
billion. Yeah.
Okay.
1.6 billion.
Yes.
Yeah.
But
The
that's my
order is,
understanding. I'm not.
huh?
That's just my understanding. I don't know.
Yeah, I think that. I mean, it's not a big deal,
Right.
but that number, the estimated time of estimated age of the sun is in the order of a billion years, which means the Earth as such was formed at obviously at the latest stage of the collapse, but that would be too late at the stage. The first human beings appeared like 2-3 billion years ago, and I remember there a billion years ago that there were some extinction, very large extinction, right?
The first life was 500 million years ago.
How?
500 million years ago, the first life on Earth.
Yeah, well, yeah. So
Okay.
at least,
So,
So it's off by.
A few
But
orders.
maybe I imagine the place
Yeah.
where you got that info is where it's from. But yeah.
I might have to. Maybe it took 30 million years for a large-scale conglomeration.
And that's it. Could be that what it means that in 30 million years the Earth as such was formed.
It goes from dust
But
to.
the actual age it goes.
Okay, thank you. Yeah, thank you. And so, maybe it took 30 million years for the Earth to form in this way. And so we move on to binary star systems. And so, the formation of a single star system seems pretty not simple so much as we take a look at our solar system and see that almost all of the planets are coplanar, and they all orbit plus or minus a few degrees on the same plane around the sun. And so we begin to wonder, well, what happens when you add another star to this system? And so that's what we'll be discussing next. And so we're going to go over the basics of a binary star system. A binary star system is what happens when protostars end up being too close to each other. And so these two neighboring protostars begin orbiting around a shared center of mass, and they'll eventually become stars. And there are a few different ways that binary star systems are identified. So there are wide binaries, which mean that the binary stars are far enough from each other in space that they're not accreting any mass from each other. And so, in contrast, close binaries are one of the stars may be accreting mass from the other, eventually may entirely swallow up a second star. Eclipsing binaries usually orbit in such a way that one of the stars will pass between the other and Earth, and so we usually be able to tell because it kind of flashes or there are changes in the luminosity of the star. You can also have circumbinary planetary disks, so a disk orbiting around both of these binary stars. And so I want y'all to keep that in mind. And so this is an artist's depiction of the planet orbiting PSR B16026. It's a huge circumbinary planet orbiting PSR B16026, which is a system with a white dwarf and a pulsar. And this is located in the globular cluster M4. So I just wanted to provide that image for you all. And so we know that there is a possibility of circumbinary disks forming around binary star systems. And so we ask ourselves, how is the physics any different for binary star systems? Well, in a single star system, there's really only one orientation in which the disk will form unless, there's any sort of very large object flying into the plane of orbit. But in binary star systems, they're a little bit more complicated as a physical system. And so there are actually two potential orientations for the circumbinary disk that are theorized. And so the first is that the disk and binary orbital planes are coplanar. So you have two binary stars that are orbiting around the center of mass, and then a disk that is orbiting around both of those on the same plane. And then the second is that the disk and binary orbital planes are perpendicular. So you have these two binary stars that are orbiting around the center of mass, and then the circumbinary disk is orbiting perpendicular to that plane.
I'm just curious, like when you solve for the binary system, would the trajectory still be an ellipse, or could it be something more fancy?
The binary star systems that I looked at, they were all ellipses, and so the binary stars each orbited around the center of mass in an ellipse.
No, not the stars, but the planets around them. Would they be still going in an ellipse?
I couldn't hear your question well. Can you say it louder? Because I'm hearing.
I'm just asking, if you have a binary star system, would planets still go in ellipses around them, or could they have are there different solutions that are more complicated?
Oh, I think that's what you meant, that in principle, there are two possibilities. You have, I guess this is what you say, correct me if I'm wrong, that, you have a star that it has its disk.
No, I understand that the plane could.
But then you have another star, that's going to be the binary, the other component of the binary, that somehow in the formation process has a protoplanetary disk that is perpendicular to the other one, or at least it's not co-aligned. And I guess that in a situation like this, I'm talking about ignorance. I don't know. I have no idea. One thing is, if the two stars were formed sort of at the same time out of the same intermolecular cloud, then probably they're going to be coplanar. But if you have two stars that will form not far from each other and eventually get captured and form a binary system, then the chances that their two protoplanetary disks are co-aligned, well, are low. I mean, it could be anything.
In fact, there is an image further down in the presentation where there is a binary system with circumbinary disks that aren't aligned. But,
That was your question, right?
He's asking if the planet's orbit is an ellipse or not in this system.
Oh, you don't believe in Kepler.
It was for one star, right?
Actually, it shouldn't be.
Huh?
It shouldn't be an ellipse because it's a three-body system. So it's not.
Oh, well, yeah, I mean,
it may look better.
yeah, I guess it depends on the nature of the binaries there.
Yeah, I don't want to interrupt this discussion. It's just, it would be an ellipse because you can approximate the binary star system with a single point mass. So it would be an ellipse. You could have a non-ellipse orbit, but it would be unstable over geologic time. So you could have two stars. It could pass in like a figure eight, but that figure eight would be destabilized because you would need perfect timing between the stars. So you don't expect to see that.
So close enough, it could be something fancy,
But over short time scale.
Listen, you know that calculate precisely the orbits of just the planets of the solar system. They do have perturbations. For example, Mercury, you need to use general relativity, but when we look at the planets, they are not the ellipses that you will get if you were thinking about a two-body problem. When you go beyond the two-body problem, nothing is a perfect ellipse anymore. But you still have Newton's laws. And Newton's laws, in that sense, are pretty reliable, unless you have very strong masses for which you need a general relativity convection. So, out of ignorance, because I know nothing about binary star system, which is a particular specialty of astronomers that know a lot about that. I think that you might have several weird cases, but like Richard said, some of them are not going to be stable, which means in the lifetime of stars, whatever those things happen, they would disappear or get smoothed out or something like that.
Last point to that effect, and I don't want to take it, you would see the ellipse maybe precess over time.
Yeah.
So that the binary star system might perturb the planetary orbit and cause it to change shape or change orientation over time. But that's over hundreds of millions of years or billions of years.
Okay, and so these are the two stable theorized orientations of the circumbinary disk. The first has been observed, and the second has been theorized but never actually observed until now. And so we assume that if that second orientation did exist, then planetary formation would be possible. So we take a second to kind of think about what it might look like to live on a planet that was orbiting around a two-star system. Well, stars, the suns would seem to move in and out of the disk plane, so that would look a little interesting, seeing that star come back and forth from you. Objects would have two shadows at the same time, and so the first image that comes to mind is that Star Wars image of the two stars in the back, and so I'm kind of thinking about whether or not they were accurate when they did the shadows in the movie. No, right? Okay. And then also the seasons on the planet would vary laterally depending on how much illumination that part of the Earth was receiving, depending on the position of the stars in the sky at that time. And so with all of these weird things going on, we ask ourselves, is it even possible for a planet to form in a polar circumbinary disk? And so that's what the paper sort of discusses. First, they wanted to go ahead and confirm that there was a circumbinary disk in this system, so they went ahead and did. Then they wanted to show that the circumbinary disk was in a polar configuration. And then they wanted to confirm that planets could potentially form in this disk. So we talked specifically about the system HD 98800. Talked about in the paper, it is a quadruple sun system, and so there are two binary star systems that are orbiting the center of mass. Actually, I'm not sure that's particularly true. Star system A is orbiting around star system B. And so they did this weird sort of naming technique in the paper, and so I just wanted to go through that in case any of you had questions. The first binary is referred to as A, and then each of the stars in the binary are little a and little b. And then the second binary system, the one that's talked about in the paper, is referred to as B, and then the stars within that system are referred to as little a and little b. And so sometimes in the paper there would be very weird sort of sentences talking about system B little a, B little b, and so it was difficult to keep track of, and so I wanted to make sure I pointed that out. So the paper focuses again on binary system B, and it's been known that binary system B had a circumbinary disk orbiting around it since the 1980s. But originally it was thought that this circumbinary disk was in a polar configuration. In several different pieces of scientific literature, it was interpreted, the circumbinary disk was interpreted to be either a protoplanetary disk or a debris disk. And so there was really no consensus about whether planets could form in this circumbinary disk. But we do know that the position of this binary system is such that the disk itself pretty much faces the Earth face on. I think the angle is somewhere around 16 degrees from the sky plane. So we get to talking about the little system that could. And so here you see this red plane here shows the plane of the circumbinary disk. This gray plane here shows the plane of the sky, and so it is at a 16-degree angle. The plane of the sky and the plane of the circumbinary disk are at a 154-degree angle. And this is the image that the scientists from the paper, or the model that they settled on when at the end of this paper. And so you can see that the barycenter direction of the circumbinary disk is sort of, or that the angular momentum vector is precessing around the barycenter direction at about 4 degrees. And so for all intents and purposes, this model assumes that, or suggests that this circumplanetary or circumbinary disk is in fact perpendicular to the orbit, to the planar orbit of that, or the binary orbital plane. Does anybody have any questions about this image? Because I know there's a lot going on. Yes?
So the planetary disk was like perpendicular, so that means that the planets would orbit
right, so
on top of them?
Well, so this is the plane of the binary star system. This is the circumbinary disk. And so the planets would be forming on this plane here, orbiting these two stars that are orbiting in that perpendicular direction. Yeah?
What are those two rings like that?
Oh, the two rings are the orbits of the stars in the binary.
How many stars?
2. I will show another image that shows the orbital path of the second binary system in a second.
Sorry, I'm confused. I'm not sure I understand. So you had two shades of gray, right, for the ellipses. So one represents?
This is the orbit of each of the stars in the
One
binary
binary.
B. Yes, this is
So
one of
two
one of
stars
them.
in that,
Yes.
moving in that ellipse.
Yes.
But you have another ellipse.
We do have another ellipse, and it's, let me see if I can find it, sorry. Right there will show the ellipse of the second
Oh,
binary.
okay, good. So that's, okay, that was.
So
my
this is just
confusion.
one.
So you only have one binary here. So there are only two stars there.
Yes, just two stars. One
And
star here,
each
one
of the
star.
ellipses belong to the trajectory of each of the stars.
Yes.
Okay, got you.
Any other questions?
What will happen if they collide each other?
The two stars?
Yeah. collide at least it is possible?
Sure.
Yeah, in principle, you would need to, I don't know if they, I don't know how close they are to colliding, but it could.
I mean, I didn't read anything in the paper about them being particularly close to colliding, but I imagine that they could, if anything ever like disturbed either of their orbits.
You'd probably destroy the star system.
I mean, but
Yes.
this system has been studied for
Yeah, it's been
so
stable for
long.
quite some time, yes.
So it's stable for now. I
Stable
mean,
for over 30 years. But
you know, in human life,
that's,
I mean,
that's
the only
that's
thing
point
that's
we're
not very stable are humans, but,
To answer your question more scientifically, you'd probably get a kick, and then you would destabilize the rest of the system. So you would probably have some net vector, it would probably shoot the conglomerate mass off in some direction and destabilize the planetary orbits.
Okay, so it will be unstable because our two stars are orbiting each other. They could in some moment collide at the right, so it could be a little bit unstable.
Yeah, it would destabilize the system probably. That would be my guess.
So we're going to discuss a little about the two theories concerning how the system came to be. The first was that the binary star system B formed with its circumbinary disk, and then at some point later in time, began binary system A began orbiting around that primary system. That's the first theory. The second theory suggests that if there were enough wildly varying range of momenta in the molecular cloud, this system could have formed and resulted in skewed binary disks. There's an image on the next slide that is important to this. And this was mentioned earlier. So the paper does mention that there is no circumbinary disk around binary system A. But there are other instances of binary systems where both of the stars have circumbinary disks around them. And this is an example from one of the papers that was referenced directly in the one I read. Again, note that both of the stars here have circumbinary disks around them. Originally, or at some point, it was believed that binary A had a circumbinary disk, but since then the disk has dissipated. And so now we're going to talk a little about how HD 988000 was modeled to get that core image from a few slides ago. I will discuss briefly the methods used in the paper, and then refer to the results that came from each of those methods that was used.
Could you go back to the slide
Yeah.
where it was talking about the torque? Yes, this one. So additional torques.
Do you have a question or?
Yeah, I'm just trying to understand, like, where this torque is coming from.
So the binary system A would come into the system such that it would produce a torque, and the disk would tilt such that, or to accommodate for that torque, and return the system into some sort of stable equilibrium.
So we first have system D,
Mhm.
and it has this, right?
Yes.
Then A comes.
Right.
And it has a torque, right?
Well,
Why? I mean, why would it? So depending on how it comes. Yeah. So it should come at an angle to come torque, right?
right.
Because if it comes like perpendicular
Right.
to the plane.
So
then
it,
would
yes,
be-
it does all depend on the direction in which A first approached.
Okay.
But they assume that, it approached from a direction that would cause the disk to become perpendicular. They don't specify what angle that must have been at, but they do say that it's possible. So that's what they do there, is they theorize that it's possible.
No.
Okay. So talking about how HD 98880 was modeled. HD 98800 was first detected using ALMA, or the Atacama Large Submillimeter Array. It was observed in 2 observation blocks. The first occurred on November 15th of last year, I believe. I didn't include the year, but I believe it was last year. And then the second block occurred on November 19th. The first block, they used 49 antennas, or 49 antennas were used to detect the system, and then during the second block, there were 45 antennas used. And then the data that was received by these antennas was then processed using CASA, which I believe stands for Common Astronomy Software Applications. CASA version 5.1, and so the applications in that package were used first to calibrate the data that was received from the binary star system, and so that was used, to improve the signal-to-noise ratio and clean up the data that was received. And then it was also used to concatenate the data that was received on both of these days. I didn't go into the specifics about how that was done, but I can refer you to the website and show you which of the softwares, specific softwares in that application package were used. So this is really cool. This is an image that was the image that resulted from the concatenation and calibration and concatenation of the data that was received from this binary system. You can see here, I know there were some questions about this binary star system B model that was shown earlier. So that model is essentially just this part right here. And so we have the first binary star system and the disk orbiting at a perpendicular to the orbit of these 2 stars here. And then we have the orbit of the second star system A, going around that original system. This image is very interesting because you can see this image right here is particularly interesting because in the next graph, you're going to be able to see that they identify the minimum radius and maximum radius of this disk, of this dust disk. I'm not sure I specified that, but this is the image of the dust disk around binary B. Any questions? Any questions about this graph in particular?
I wanted to ask, how, are the chances of 2 binaries coming into contact pretty high or low, in a planetary nebula? For 2 of them to discover.
I'm not particularly sure. Is anyone else? Does anyone else know? Okay. I don't know, but that's a good question. Right, so there's that image. Again, this is the image of the dust disk forming around binary B. This is an image of both the gas cloud that they were able to identify around binary B. And these lines show the inner radius of that dust disk and the outer radius of the dust disk. So they were able to show that the gas disk is relatively asymmetrical. The north end, they were able to determine that the north end is the end that's pointing, rotating towards us. Though they cannot tell whether this is rotating clockwise or counterclockwise. Again, because I mentioned it earlier, this disk is relatively planar in the sky plane. So we can't tell whether it's rotating clockwise or counterclockwise. Again, the contours determine the rough edges of the cloud disk. And that's really important to point out because one of the other questions that the scientists were trying to answer was whether or not this was potentially a protoplanetary disk. And so they went ahead and theorized that at some point the gas and dust would have been evenly spread out over this entire area. But you can see from the inner and outer radii as limits for that dust disk, that this seems to have been moving inward. And so that means that potentially these dust particles have been growing heavier, which is the first step in planet formation and moving towards that protoplanetary phase. And so they use this graph to show, that this is in fact protoplanetary, and the one before to show that the system was most stable in a polar circumbinary orientation. Any questions about this graph? No?
Is that rate of velocity or I mean, what are the colors?
Oh, the colors are, the colors show the intensity weighted carbon monoxide velocity. So the colors show intensity weighted carbon monoxide velocity, and the contours show the inner and outer limits of that dust disk. If you want to read up on more of the methods, they were very in-depth. You can go ahead and look for the paper. It was published in Nature Astronomy. This paper here was where that image of the binary systems with skewed protoplanetary disk was taken from. So if you'd like to go ahead and take a look at that. And then again, if you want to look at the specific applications that were used to model the system, you can go ahead and visit the Common Astronomy software applications